thank you everybody for coming out for another one of these Zoom webinars. So today's topic is going to be all about cross-country flight planning. All right. So just as an intro, my name is Wesley Chin. I'm a CFI at the Princeton Flying School, and I've been teaching here for about 10 months so far. I also did all my certificates and ratings at Princeton, all the way from private through CFI. When I'm not teaching at the airport, studying at Rutgers Business School, studying finance there, starting my junior year, and I also teach saxophone and piano. All right, so before we kind of get into like a sample scenario using the Nav Log and everything, we're just going to go over a couple of terms that we use to describe, like headings and all this stuff. We'll talk about that, and then we'll get right into like a whole cross-country planning scenario that we're all going to kind of work on it together. I got someone is entering their waiting room. All right, Andrew Bird, let me admit him here. Is that my job? Okay, did that work?
Yeah, he's in. You're good.
Sweet. All right, so we'll, awesome. All right, so we'll continue here. So yeah, we'll start off with the navigation terminology, and then we'll go into that scenario. So we'll plan a sample cross country from Princeton to Scranton is kind of one way there. All right, so we'll get started here with some navigation terminology. Okay, so the first term I want to talk about here, something called true course. We're going to abbreviate that to C. True course is just your direct flight measured on a chart from true north. So, we haven't corrected for any variation or anything. Course is like another word for track. And basically, this is just like the line your airplane is drawing over the ground. Nothing's corrected for wind or anything. It's just, straight line from your airport to the destination over the ground. That's your true course there. Second thing is true heading. All right. So we still haven't, added in any magnetic variation. So it's still, respect to true north. But now we're, correcting for some kind of wind. So true heading is the direction the airplane's nose points with respect to true north. So basically, to convert to true heading, right, we're starting off the true course, which we'll measure on the sectional later on. And then we add or subtract some kind of wind correction angle to get your true heading. So basically, the concept is, course is just your direct track over the ground, and heading is that course corrected for wind. All right, so that's true course and true heading there. Next, we've got magnetic course and magnetic heading, and it's, again, pretty simple and similar principle here. So magnetic course is your true course corrected for magnetic variation. So variation is basically the difference between true north and magnetic north. It's going to be a constant number in terms of at least like flight planning, and I'll show you guys where we can find that on the sectional chart. And then magnetic heading is your magnetic course corrected for the wind again. So it's a pretty similar thing. Same thing what we just talked about before, how like course is your track over the ground and heading is the direction your nose is pointing in. So basically course corrected for wind. However, instead of values being true, it's all just magnetic now. We're adding in that magnetic variation. So that's kind of the only difference there. So another way to put this, right, to get from true to magnetic, we are either adding or subtracting some kind of variation, right? And then course to heading is, again, adding or subtracting some kind of wind correction. So two more important ones here. So the ultimate goal for us is to find the compass heading, the CH. When we actually have to fly in the airplane, right? This is the aircraft heading read from our compass, right? So we start off with true course measured from the sectional, and we work our way through to get compass heading, CH. Another definition for this is magnetic heading corrected for deviation. So what exactly is deviation though, right? So, when the airplane's running radios are on, it's going to interfere a little bit with your magnetic compass. So deviation is just like slight compass errors due to that kind of magnetic disturbance from electrical parts in the aircraft, right? And to correct for any of this deviation, each airplane is going to have like a little compass correction card, a compass correction card. All right, let me just admit someone else in here. Okay, the compass correction card is usually found somewhere near the magnetic compass or in the airplane, and it'll pretty much tell you exactly what you have to do. So it'll be like, if you want to fly 330, steer 331. So your deviation in that case is just +1, only adding 1 degree. All right, so that's the goal there. We're starting from true course, getting all the way to compass heading. All right, so that's your navigation terminology. Just a couple other things that we're also going to use in the Nav Log, some atmospheric terms here. So standard atmosphere, right? So standard pressure at sea level is going to be 2992 or 29.92 inches of mercury there. So that's a pretty important number to know. And then your standard temperature at sea level is going to be 15 degrees Celsius, 15 Celsius at sea level, right? Now, pretty important to know those two, but there's also something else that's we're going to use later on, a lapse rate, right? So we have a standard temperature lapse rate in the atmosphere. So we can say that in a standard atmosphere, temperature will decrease 2 degrees Celsius, decreases 2 degrees Celsius for every 1,000 feet gain in altitude, all right? So for example, if I'm at sea level, we know that should be 15 degrees Celsius on like a standard day, right? That means if I go up, I climb 1,000 feet, the temperature will decrease 2 Celsius. I should now be at 13 degrees Celsius, and that'll be standard there. I keep going on, 3,000 feet would be 9 degrees Celsius on like a standard atmosphere day. We also have a couple different terms and types of altitude over here. So if anybody watched I think it was like a flight instruments webinar, we kind of talked about each one of these 6 packs and what we're reading on them. So with the altimeter, right, we've got a couple different types of altitude to understand, and we'll also use some of this in our Nav Log, right? So the first one, we've got something called indicated altitude. Pretty simple to explain. This is just whatever you're reading off the altimeter, right? Second, we have true altitude. True altitude is another word for MSL, just above means sea level, right? And we have absolute altitude, AGL, above ground level. So, for example, elevation at Princeton, right, is 128 feet. That's in MSL. But if I go to the ramp right now and go sit in 2 Fox Whiskey, sitting in the plane, not doing anything, my AGL, my absolute altitude, is 0. Right, because we're right on ground level there. But my true altitude would be 128. We got something called the pressure altitude as well. So the book, or all the FAA textbooks, gives some kind of weird definitions. I think they say height above standard datum plane, which is correct. Another way we can put is if you go to the airplane right now and set in 299 or 2 in the little Colesman window there, whatever altitude you're reading is going to be the pressure altitude. We're going to use this formula in red here later on to get different information for the Nav Log, and this is what we can use to calculate pressure altitude. So 29.92 minus the current altimeter setting, and you're going to take that value, multiply by 1,000, and then add your elevation. So I'll have that written down later on as well, but we're going to use that for pressure altitude. And finally, the last type of altitude, pretty important term to know, especially in this season here, we got density altitude, all right? So density altitude is your pressure altitude corrected for non-standard temperature. In other words, it's like the altitude at which the airplane feels like it's flying at, right? So when we're at a high density altitude, it's high outside, high humidity, we're in higher elevation, air is less dense, right? The airplane's not going to perform as well in that higher density altitude. All right, so last thing here, we've got airspeeds, different types of airspeeds, and after that, we'll go directly into our little scenario here, right? So 4 types of airspeeds we'll talk about. First one is indicated airspeed, IAS, or if it's knots of indicated airspeed, it would be like KIAS, right? This is just like whatever you're reading directly off the airspeed indicator. Second is calibrated airspeed, CAS, or if it's in knots, right? KCAS. This is your indicated airspeed corrected for any instrument and installation errors. If you look in your POH section 5 for performance, at least in the 172, right, the first table or chart is like an airspeed calibration chart, using normal static source to get from indicated to calibrated. So we're going to use that a little bit also. 2 other ones that are pretty important. We have true airspeed, TAS. True airspeed is the actual speed of the airplane through the air, whereas ground speed, GS, is the speed of the airplane over the ground, right? In other words, that's your true airspeed adjusted for some kind of wind, right? So, if I'm flying with a tailwind, for example, that ground speed is going to be a little bit higher, and then vice versa. So that's all the terminology I kind of wanted to review before we get into this scenario, right? Okay, so let's talk about the sample cross-country scenario. So materials needed for cross-country planning, quite a bunch of things. Okay, first thing over here is a VFR navigation log right on top. So we're going to use this in Excel. We're going to fill this out together, and we put a lot of different information on it. Different checkpoints along the way, altitudes to fly out, winds aloft, true airspeeds, headings, distances, fuel burn, timed, airport information. All that stuff is going to go on your navigation log, like a one sheet of everything you need, pretty much. On the top right here, you also want to have a current sectional chart for the area which you're flying in, right? I know this is not New York. I don't know where I got this. This is Nashville there, but all right, we're going to use SkyVector today for that. Bottom right, we've got the POH, or the information manual for your airplane. We want to have a copy of that because we're going to use a couple of those charts in there, such as the cruise performance chart, some different climb performance charts as well to fill in some of the information. Next to the left of that is a CX3 flight computer. This is what we use in the Princeton Flying School ground kit for all the calculations for cross country. If you have one of the paper or manual E6B, same kind of thing. It's going to work the same. You also want to have a chart supplement, again, that's current and valid for your area. We're going to find airport information in there, such as frequencies to talk on, pattern altitude, elevation, all that we can look for there. But again, I'm going to use SkyVector for that. And finally, the plotter on the left side. So a couple uses for the plotter. First thing, we're going to use that to measure true courses directly off of the sectional chart. And we also use it to measure distances, right? Because we have to know how long it takes to get from your second to third checkpoint, for example. So we use the plotter there, making sure you're using the sectional chart scale in nautical miles. We'll use that to measure distances. All right, so we'll get started with our scenario. So we're going to plan a flight from Princeton to Scranton. And we'll, I guess I decided to do an 8 Mike Charlie over here. All right. So what I'm going to do, I'm going to switch to Excel here. We'll get this open. All right. Can everybody see this Nav Log here? Awesome. Okay. So again, this is like a Jeppesen Nav Log. I think all I searched up on Google was VFR navigation log in Excel, and this is the first thing that came up. There's like a PDF of it as well that I usually end up using. So we're going to fill this out together. The other thing that I sent in the chat was a Word document for steps we can use to complete this nav log, right? So what I'm going to do, I'm going to open that up. I'm going to show you guys where we're going to start here. Okay, so the first couple of things I'm actually going to skip over. We're not today going to talk about like the pre-flight weather briefing. We're not actually going to do it here, all the pre-flight action and stuff. We're going to assume, all right, we've got your weather briefing. You've done all the pre-flight actions that are required by the FARs, and you've decided to make a go decision. You're going to go on the trip, right? So we're going to start over here at the fifth step. And I have down plot course on sectional chart and pick checkpoints somewhere between 10 to 25 nautical miles apart and fill it in on the nav log, right? So when I'm flying, good distance like this, maybe 70, 80 miles, I'm probably not just going to go straight. I'd like to have maybe a couple things along the way just to verify, all right, am I actually going in the right direction or am I not? So we're going to look for some checkpoints, things that are nice and easy to see, maybe some airports along the way, body of water that could be easy, town, maybe just something on the sectional that has like a flag on it, which indicates it's a VFR checkpoint. That could be good there. But basically, what we start off with is just drawing a straight line on your sectional chart from your departure to destination airport, and you start looking for things along the way, maybe 10 to 25 miles apart. So some things you also want to consider though, like when you're picking your checkpoints, airspace, are you flying through any restricted airspace, something like that, terrain, any obstacles that are too high, diversion, alternate airports, all that kind of stuff. So let me actually switch back to Google here, and we're going to go to SkyVector. So for those of you who don't know what SkyVector is, just an online site that we have all your aeronautical charts published on. You can also find like your chart supplements for each airport here. So another good source if you don't have foreflight or anything here. So what we're going to do, the way I can draw a straight line here, I'm going to type in, I'm going to open the flight plan up here. Departure airport is going to be 39N, and we're going to go to Scranton, which is Kilo Alpha Victor Papa. All right, and now it's giving us a nice straight line between those airports. So you would draw this, on your sectional paper chart there. So let's start zooming in at our sectional and looking for some good checkpoints over here. The limitation of this, I don't think I can figure out how to like show the scale of what looks like about 10 miles or what's 5 miles here. But just as a reference, if you guys see Princeton and Solberg right over here, I think it's like 10 to 11 miles or something like that. So that can be a reference here. All right. Anybody want to start picking checkpoints for me here? So we've got a bunch of different things along the way, right? So we're going to try to keep it a straight line. So, you can be like, oh, left of this airport, right of this, body of water, whatever, something like that can work. But look for things that have like flags on it, because those are nice and easy to see. The FAA already said that. An airport could be good too, anything like that. So I'll leave in this area for here. Does anybody see anything along the way that could be a good checkpoint? All right, I got a message here from Umar in the chat. The turnpike. Okay. Let's see. So I'm not sure which turnpike we're talking about right now, but the New Jersey Turnpike's over here. We could have some other roads over here. All right, Joe said, I believe the compass roads around the VORs are 10 nautical miles. I actually did not know that. That's a really, really good tip. If so, thank you for providing that. Awesome. Left of Round Valley. All right, Sarah, that looks pretty good there. I agree. And Spruce Run. Yeah, you got it, Omar. I'm just curious, are you guys able to unmute yourself, or is it like a limitation? I don't know.
They can unmute themselves.
Oh, okay. All right. So knows when to talk. Okay. Okay. So we have left of Round Valley from Sarah, and then Umar says Spruce Run. I think those are two very good choices. If you guys have been flying in the area, I'm sure you know those are extremely easy to see from the air. So let's see how far these guys are. So if I put, let me try like Spruce Run here. So Spruce Run could be a good option too, just because it has like the flag over here, which indicates, oh, it's a good visual checkpoint. Maybe if someone doesn't know the area, they wouldn't choose Round Valley, but we know, that's a great option there. So, all right, I'm going to see what Spruce Run is in terms of like the distance here. So I'm going to put a little mark there. And SkyVector is telling us that's 19 nautical miles, which works out pretty well, right? That's, somewhere between 10 to 25. So let's see that. Spruce Run will be our first checkpoint there, nice and easy to see, and we're going to go right on top of it. Awesome. Okay, so I'm going to scroll up a little bit more here. Any other checkpoints that we see along the way? Things with flags, some we're flying over near an airport, anything like that? Sarvan, excellent. Yeah, this little town right here at Bangor is very good. There's a flag over there, so why don't I mark that? Another good view of our checkpoint. And let's see what the distance is. 20 miles. All right, it's working out pretty well. We've got some pretty nice equally spaced checkpoints. All right, and there's Scranton, and we've got Bangor over there. So probably just one more in the middle to kind of fill the gap. Anybody have anything around here? All right, Umar says Pocono Raceway. Looks like a good choice there. So right over here, it says Pocono Raceway. And again, it's got like a flag. And yes, you got it, Umar. Mount Pocono, Pocono Mountains Airport. MPO is also off to the right side. Also nice and easy to see. So it looks like our course or the track here is taking us directly in between the Pocono Raceway and Pocono Mountains Airport. So how about I put a little checkpoint here? Let's see how far it is. 16 miles from Bangor and then 19 miles to Scranton. So perfect with the distance there. I think it looks good. So like when we type that into the Nav Log, we could write, for example, left of MPO or right of Pocono Raceway, whatever you kind of want to phrase that as. All right, so that looks pretty good for our checkpoints. We've got some nice equally spaced ones, all good there. So what we're going to do now, let me just briefly hop back to this document just to show you one more thing. So we got our checkpoints. Subpart B of this step, I wrote, include a top of climb checkpoint after the departure and then a top of descent, TOD, checkpoint before the destination airport. It's a good idea to know where those two things are going to be, especially top of descent. So what we're going to do, we'll just type it in right after in the Nav Log here. So let me open that Excel file again. And right over here, we're going to basically fill this in left to right. Okay, so aircraft number, why don't we type this in first on top? We are, or if we're flying, 8 Mike Charlie, I think. So but 298 Mike Charlie, all right. And we're gonna start filling in these checkpoints now. So first one is our departure airport. We are leaving from Princeton, 39N, so go right there. Cool. We're gonna put a top of climb checkpoint, TOC, and now we're gonna continue filling in what we had on SkyVector, right? So I think the first checkpoint that you guys chose, which is really good, is Spruce Run. So why don't I type that in here? I think we're like directly over it. And after Spruce Run, we had that town, I think, over here that Sarvan chose. We're going to fill that in. And then one more Umar had was to the left of MPO, and then the right of the raceway, I think. So we'll put that in there. And then we're going to include a top of descent, TOD. And finally, we'll put in our destination airport of Scranton, AVP there. So there's all our checkpoints, all inserted in, boom. All right, so now we're gonna continue filling everything out here. So we're gonna return back to the steps here to follow. So we've got our checkpoints, awesome. And we're gonna go to step 6 now. What altitude are we gonna fly at? So we've got to decide a cruising altitude. So unfortunately, we can't just use whatever we want. So the FARs have this rule here, based on the direction of flight, we choose cruising altitudes if you choose on flying above 3,000 above the surface, right? Little acronym we can use to remember that is NEOD SWEVEN. I don't know if you guys heard of that, but that's something that you can use, right? But basically, this little chart here is pretty helpful to determine what I just said. So let me kind of make this a little bigger here. So the direction of flight, this is going to be all based on your magnetic course. So it's what you're flying over the ground, and you add the variation or subtract it, you know. So if you're going to be flying a magnetic course between 0 to 179 inclusive, you've got to fly an odd thousands altitude plus 500 feet. So since this is only above 3,000 AGL, that could be 3,500 or 5,500, 7,500, and so on, right? Now, if you're on the other side of the circle, 180 to 359 degrees inclusive, and that's magnetic course again, this is going to be even thousands plus 500. So 4,500, 6,500, 8,500, and so on, right? So we can use this little chart to help us determine, all right, what altitude should I be flying here, right? So let me just return to SkyVector here. And just by looking at this line, I think it's hopefully pretty clear what we should choose. So it shouldn't be kind of too much of a debate here, but it's either going to be on the 0 to 179 or the 180 to 359, the odd or the even thousands. So can anybody pick a cruising altitude for me that would work here? What do you guys think?
4,500.
4,500. All right, I like that there. That's going to make perfect sense, right? That's on the even thousands plus 500. If we go back to our little chart, that's definitely where a magnetic course is going to lie. So we're going to fill in 4,500 feet for our cruising altitude. Some couple other things to also like pay attention to terrain and obstacles along the way, but definitely because these minimum elevation figures we see, we don't have to worry about that. So 4,500 feet will be good, but we're also going to take note of this here. For that last altitude box, when flying from top of descent to the destination, what I usually like to do is to fill in the pattern altitude because we don't intend on staying at cruising altitude by the time we reach the airport, hopefully. Okay, I got something in the chat here. I'm still in pain from the NEOD SWEVEN. The N and the S in that don't have significance, do they? It's pretty funny there. That is a very good point. Honestly, no, they really don't. It's just the east or the west side, but in the beginning, you know, sometimes for some people it's a little harder to grasp, but yeah, it really is just E and W. So if you want to make it EOD weaving, go for it there. All right. So what is it saying? Okay. So I forgot. I think we had pattern altitudes. Is that what I was talking about? Okay. So yeah, when we're flying from top descent destination, I like to fill in the pattern altitudes, right, for that altitude, because we're not going to stay at cruising altitude by the time we reach your destination. So the standard traffic pattern altitude usually is, at least for light airplanes, right, 1,000 feet above ground level. But you can also check your chart supplements, right? So you can check your chart supplement. Sometimes they'll give like the pattern altitude for certain airports in the remarks. Let's see here. So what I can do, we can go to SkyVector, and if I go over to Scranton and click on the airport itself, I can get a new tab with all this great information, and here's the chart supplement, which I can open. So it's telling us right here that the elevation for Wilkes-Barre Scranton is 962 feet, so remember that. And if we look at the airport remarks, sometimes you'll see pattern altitude, sometimes you won't. Looking at this, I don't see a pattern altitude listed for us. So what we're going to do, we're going to say 1,962 for pattern altitude, right? Because that's your elevation, and we're going to add 1,000 feet to that. So we'll fill that in. All right, back to the Nav Log. Altitudes is next here, so your altitudes column. So we're going to fill in 4,500 for all of the boxes except the last one here, right? So from top of descent to Scranton, we're going to go down from 4,500 to 1,962 feet. Now I'm sure you guys are going to ask, do we actually have to fly that in the pattern? Well, Everybody is not great at maintaining altitude anyway, so it's going to be somewhere around 1900, 2000 the whole time anyways. Works out fine. Okay, before I continue on, Andrew says, east is least is another one to use there. Yeah, that's a good acronym. East is least, west is best there. I'll usually use that one for like the magnetic variation. So that's something we will talk about very briefly, but very good, very good. Okay, so we've selected checkpoints and we've got our cruising altitudes. Awesome. So going back to our list of steps. Next up, step 7, we've got to fill in our winds aloft. So what exactly is winds aloft, right? When we are calculating headings to fly in the airplane, we're not going to use the winds that are at surface because it's going to probably be a little different at 4,500 feet. So fortunately, we do have a forecast on Aviation Weather Center that we can find that'll tell us like different winds at different altitudes at different airports. So we're going to use that here. You can also receive this information when you call the weather briefer or when you do your online briefing on 1-800-WX-BRIEF. You can also show it, but I'm just going to show you guys directly from Aviation Weather Center. So, all right, I think I had it open somewhere over here. Let me refresh this. Okay, so I went to the page directly, but let me just show you guys where to actually find it. So aviationweather.gov, this is the home page here. To find the winds aloft, we're going to go to forecasts and winds and temps. So this is what we're looking for, but they kind of give it to us in this like, I don't know, map. Not really a fan of this, but we can go to the data over here, text data. 2 things. So now we've got to select the correct region, right? So we're going to go here and select the right one. We're flying in the Northeast, so we're going to choose Northeast. And we've also got to select the right time span, right? We don't want to be using winds aloft for a different time span that we're not flying in. So let's say that we are departing, how about 9 p.m., which is in 30 minutes, right? So does anybody know how to convert 9 p.m. to Zulu time? 9 p.m. local Eastern right now. Anybody know how to convert that?
Add 4 hours.
Let me see here. Yeah, so like what we would do is the answer would be 0100 Zulu. It's like the day before. So what would 9 p.m. be in 2400 time? Can anyone tell me here?
1700. Wait, no, 21.
2100. Yeah.
Yeah, exactly. 2100, right? Good. So right, and Umar, that is exactly right. Then you would add the 4 there, so 25. But of course, that's not going to go to that. So we're going to go to the next day. So yeah, it is weird. It is 0100 Zulu in the next day. So we'll stick to this time span here. So we'll choose that in Northeast Boston. Cool. So this is the correct data that we want to use now. So first off, this column on the left side is like the airports that they're giving us information for. You're not going to have winds aloft data for every single airport, not every location. So you kind of just have to look if something's close to our route. We're going to Scranton, and Scranton is actually listed here for the winds aloft. So we're just going to use that actually. Right over here, AVP. So we're going to use something in this whole row. They also give it in terms of different altitudes over here. So like at 3,000 feet at Scranton, it's going to be 180 at 17 knots, and 6,000 feet, it'll be 230 at 15 knots. And then this next number, plus 15, is saying it's going to be 15 degrees Celsius at 6,000 feet. So we know we're going to be cruising at 4,500. So what we can do is interpolate or take the average of these 2 values, right? So why don't we try that here? So we know 3,000 feet, right? It's going to be 180 at 17. 6,000 feet is going to be 230 at 15. Can anybody tell me what the winds are when we interpolate or average should be at 4,500? So let's do a little bit of math here.
It'd be about 205 at 16.
Beautiful, exactly. 205 at 16 knots. Awesome. So we've got our wind direction and velocity. So why don't we fill that in at least for the first box for now. So 205 in the direction and 16 knots for the velocity. Cool. And then on the bottom, they're also asking for temperature, right? So if we go back to this winds aloft data over here, they just told us they're at least forecasting at 6,000 feet over Scranton, it's going to be 15 degrees Celsius. They don't give it to us though at 3,000, and so obviously we don't have it at 4,500 either, right? But we know, like we were just talking about before, that standard temperature lapse rate, right? For every 1,000 feet you gain, you should be losing 2 degrees Celsius. So you can use that information to kind of figure out what it probably is at 4,500 feet. You could also work the other way around if you have a METAR, just go up, but we can try this. So Anyone want to try using that lapse rate to determine what the temperature will be at 4,500? So yeah, you lose 2 Celsius every 1,000 feet you gain or go up.
Like 9 degrees or so?
Say that again for me, Umar.
So you'd lose about 9 degrees?
So you would lose 2 degrees Celsius for every 1,000 feet gained, right? So if I'm at 6,000 feet and they're telling us it's 15 degrees Celsius, let's see. If I go down 1,000 feet to 5,000, then I would increase 2 Celsius. So 5,000 feet. What was that? Oh, my watch just decided to convert that. Okay. So yeah, 5,000 feet would then be 17 Celsius,
17.
right? Since we're now losing altitude. So what would 4,500 be?
Yeah, around 18.
Yeah, you
You're
got
going
it.
to
So it'll
gain one
be
more degree.
18.
Yeah.
Perfect. You got it, Andrew. Exactly. So we're going to say at 4,500 feet, it'll be 18 degrees Celsius. So we're going to fill that in there. So personally, we're going to stick with these winds and temps values for the entire thing. I did write a little note though in the steps, I think. I've seen some people like for their departure top of climb and then top of descent to destination actually like interpolate between the winds and a METAR and then winds aloft if you want to be super accurate. Probably not going to make too much of a difference because you probably have the airport in sight by that time. So just something to throw out there. But yeah, we're going to keep these exact same winds and temperature values. So let me copy this. We're going to put this all the way down there. Awesome. And that's our winds aloft data inputted. Okay, so we're going to keep moving along here. So we just did step 7. Step 8 and 9 is all about filling in that true airspeed column, right? And to do this, we're going to start using a couple of charts in the POH, right? So let me just get out of this here. So a couple of different things to point out first. The true airspeed for your first leg, Princeton to top of climb, is going to be different from everything else, right? We usually are not going to climb at the same airspeed you cruise at. So we're going to leave that one blank first, and we're going to fill in all the true airspeeds for the bottom here, right? So to do that, first thing, we're going to go open up the POH here to the cruise performance chart, and that's in section 5. Let's see, so I have that open here. Okay, if you want to be extra precise, looks like it's 5-17. Okay, cruise performance chart. So what are we getting from this here? So first thing, couple conditions. We are at 2,450 pounds and we are at the recommended lean mixture at all altitudes. So it's basically telling us to follow those normal procedures there. So the way this chart works, first thing, we choose a pressure altitude and then we choose an RPM setting. After that, we've got all this data and then we've got to choose if we're either 20 Celsius below standard temperature, standard temp, or 20 above. So first thing, let's figure out the pressure altitude at cruising, right? So we decided, I think Gab decided, right, we're going to cruise at 4,500 feet, but that's not exactly the pressure altitude. We've got to figure that out. And to do that, I don't know if you guys remember, we had that formula I had written down earlier, right? So let me pull that up in the Word document right here. So it's 2,902 minus your current altimeter setting, multiply that by 1,000, and then add the cruise altitude. So why don't we do this? Let me open up the Trenton METAR here, right over here. Okay, make sure we refresh it nice and current. Okay, this top line is our METAR, the current observation at Trenton right now. Anybody tell me what the altimeter is at Trenton?
3016.
Awesome, you got it, Omar. Altimeter is 3016. So we're going to use that information now, plug that into the equation, and we will get our pressure altitude, right? So let me pull that up for you guys again here. So I'm going to replace this with 3016. And then cruise altitude was 4,500. So let's do this math together. I'm going to do it on my calculator on my phone here. All right, can anybody tell me what our pressure altitude is going to be?
$4,260.
All right, 4,260 feet pressure altitude. That is correct there. So we're going to remember that number and we're going to come back to the cruise performance table, right? So they give us a couple options, 2,000, 4,000, and 6,000. I'd say the 4260 is pretty close to 4,000. If I had like maybe a pressure altitude of 4890, maybe I'd like airplane between 4,000 and 6,000, but for the purposes of this, we're just going to stick to 4,000 feet. So good, we're going to use something over here, right? Next, we've got to decide, well, what RPM are we going to use here for cruise? Why don't we say 2,100 RPM? I think that's pretty standard there, right? So 4,000 feet pressure altitude, 2,100 RPM. We're going to use something over here, right? So now, last thing we got to decide is, are we 20 degrees Celsius below standard temp? Are we at standard temperature? Are we above standard temp at our cruising altitude, right? So again, this is where that lapse rate is going to come into play. We just figured out that on our winds aloft and Nav Log, at 4,500 feet, it's going to be 18 degrees Celsius. So what we can do now, we can use the lapse rate and determine the standard temperature at 4,500 and compare those two numbers. And after you can compare those two numbers, then you can determine which one of these columns you should be reading in, right? So everyone, let's see if we can use that lapse rate, right? Remember, we lose 2 degrees Celsius every 1,000 feet gained and figure out what is the standard temperature supposed to be at 4,500 feet. All right, so remember, we know sea level is 15, 1,000 feet should be 13, 2,000 feet is 11, and so on, all right? All right, anybody? Do we have the standard temp at 4,500 feet?
6.
6. All right, you got it. There you go. So it's gonna be 6 degrees. Yeah, it is. I don't enjoy doing those calculations. So yeah, it is 6. All right. So 6 degrees Celsius is the standard temp. But we said, oh my God, it's gonna be 18 degrees. That's much higher. So it's actually 12 degrees Celsius above standard temp. So what we can do is they have either standard or 20 above. Why don't we interpolate between those two values, right? We'll say it's 10 degrees above standard temp. So let's note here. Standard temp, our true airspeed, KTAS, is 105, and then 20 above, it would be 103. So we're going to say our true airspeed is 104 knots. That's the average there. The other thing we care about is the GPH, gallons per hour. How much fuel are we going to burn here? At standard temperature, 7.1 gallons, right? And then 20 Celsius above standard temperature, 6.8. So again, if we take the average, it becomes 6.95. We're going to call that 7. Nice and easy number, 7 gallons an hour. So before we add that into the Nav Log, one more note on the bottom here. Cruise speeds are shown for an airplane equipped with speed fairings. Without speed fairings, decreased speeds shown by 2 knots. We do not have that on Aim Like Charlie. So what we're going to do is we're going to do 104 minus 2. And our final true airspeed that we're going to enter in for cruise is 102 knots. So let's put that in here. True airspeed, we're going to leave the first one blank since we don't climb at that, but everything else we're going to fill in 102. And the other bit of information that we had was our GPH, gallons per hour, which is like right on the top right. So I'm going to fill that in 7.0. That's going to remain a constant number for us to use later on. All right. Very good. So that's the true airspeeds for cruise, right? But now we've got to figure out what's the true airspeeds going to be for climb, right? So there's actually another little table we can use in the POH right before the cruise performance one, which makes sense, right? This one is called time, fuel, and distance to climb at 2,450 pounds. The conditions are you're at flaps up, full throttle, and it's standard temperature. So the way this works here, we've got to figure out how much altitude we're actually climbing, right? You know, for example, if I'm leaving Mount Pocono, which has an elevation of almost 2,000 feet, and I'm going to 3,000 feet, I'm not going to use this 3,000 feet pressure altitude. I'm only going 1,000 feet up, so I'm going to use this, for example. Okay. After you figure out how much altitude you're climbing, then you just go read straight across and be like, okay, I'm going to climb at 77 indicated. It's going to take me 3 minutes, 0.7 gallons used fuel. And this last number, we're actually not going to care about. It's saying, yeah, 4 nautical miles distance, but this is all based on 0 wind. And there's always, well, not always, but there's probably some kind of wind we got to correct for, right? So we're not going to use that number. A couple other notes. We're going to add 1.1 gallons of fuel for engine start, taxi, and takeoff allowance. So we're going to write that on like a notes section probably there. Okay, so let's first figure out how much altitude do we actually have to climb here. If we're leaving Princeton and going to 4,500 feet. So the way I have this written out, we can determine the pressure altitudes both at cruising on ground and then subtract the two values to determine the altitude we gained. Alternatively, we shouldn't have to do that if the altimeter settings and all the pressure, at least the correcting factor is the same. So why don't we just do that in this case, since it'll still be the same setting. So 4,500 minus our elevation of 128, 4,372 feet is how much we're actually going up, right? So again, it's probably not going to change what we're using here, but we'll stick with, we'll call it 4,500 for the pressure altitude, and we'll take the average between these two rows, all right? So our climb speed and indicated airspeed is either 75, 76. We'll call it 76 in that case. It's going to take 7 minutes. That's the average. And we're going to burn 1.65 gallons, right? Since again, that's the middle there, but we'll call it 1.7. How about that? So why don't we fill in the time and the fuel at least for the first leg for the climb? We can add that in while we're at it. So back to Excel. Remember, this first row is for Princeton and top of climb, and ETE is estimated time and route for that chart is telling us it'll take 7 minutes to climb. So I'm going to type that in. And then fuel, we took the average, it was 1.65. We're going to make it 1.7 just so it's easy to add everything later on. Okay. So going back to the POH, the other information we were looking for was the airspeed, the true airspeed we have to fill in, right? So they give us indicated though. So how exactly do we correct for that, right? So we're going to say 76 indicated airspeed for the climb. And we can remember this number here and go all the way to the beginning of this section. I mentioned earlier, there's actually this calibration chart for the airspeed. And this is going to get us to calibrated. So in flaps up condition, it's saying that if you're 70 indicated, the calibrated airspeed is also 70. If you're 80 indicated, you calibrated as 79. Our number is 76 indicated, kind of in the middle. So we will call it, let's see, how about 75 calibrated? It's probably not going to make too much of a difference here, but we'll call it 75 calibrated, right? So now that we have calibrated airspeed, we can now use our CX3 and figure out what the true airspeed is going to be for that climb. So let me get that all opened here. Okay, here's our little online CX3 we can use. So we can go to the airspeed function here and fill some of this stuff out. We're looking for true airspeed, but we have some other things. OAT, outside air temperature. We do have this, right? I'm going to set the unit to Celsius. And we said 4,500 feet is going to be 18 degrees Celsius. I'll type that in there. We have calibrated that we just got from our chart was 75. And P out, pressure altitude that we just calculated from cruising. I should have wrote down that number. Does anybody remember that pressure altitude at cruise? I think I had was it 4260?
Yeah,
I think so.
60.
Excellent. Okay. So we're going to type in 4260 there. Boom. Everything with this equal sign is an output. So we're looking for TAS. True airspeed is 81.49 knots. Am I going to write 81.49 in Nav Log? No, I don't really care that much to be too accurate. 81 or 82 in this case doesn't matter. So we'll since it's below 0.5, we'll call this 81. All right. So we're going to fill that in there for the true airspeed now. And we've got all the airspeeds in. So excellent. We're just going to keep working in to the right. So the next steps now, step 10 is all about filling in courses, headings, and all this stuff, right? We're going to start off over here for the first leg. TC, that's your true course. That's whatever you're tracking right over the ground, no wind, nothing yet, and not even magnetic variation. So how exactly do we find true course? This is where your plotter comes into play, right? So you can use your plotter, lay it on your paper chart and measure your true course directly from that. I can't really show that in this webinar, but what I'm going to do is just go to SkyVector, and we're going to make SkyVector tell us what our true course is. You can actually click Nav Log over here. I know you're probably like, well, why am I teaching this? But oh well. Okay. We'll say 320, I think is what I got earlier. So 320 will be our true course. But again, you would use your plotter and on your sectional to measure the true course. Okay. 320, true course, all good. Next, we've got to fill in true heading. But to get true heading, there's a wind correction angle. Remember that, right? Heading is the direction your nose is pointed in, that corrects for wind. So we've got to figure out how many degrees do we have to point our nose in either left or right to make sure we fly that course over the ground, right? To do this, we're going to use our CX3, and we already have all the information to do so right here. So if we go back to the CX3, I'm going to go to the wind correction function. We're going to enter here. I'm going to clear some of the stuff out just to make sure we don't have any leftover data. So we're going to fill in the true airspeed. 81 is what we wrote in. I think it saved it from last time. We'll just leave it there, 81.49. TCRS, true course, we do have that, which is 320. We're looking for the heading, but we're going to fill in the wind speed, right, which was 16 knots here, and direction is 205. Once I do that, I'm going to get the rest. Everything with that equals an output. So WCA is your wind correction angle, minus 10. So it's saying you've got to point your nose 10 degrees to the left to get a heading of 310 if you want to do that true course of 320. So we have true course 320, subtract 10 to the left for your wind correction angle, and you get a true heading of 310. So now we're going to fill that in here. So wind correction minus 10, which gets me a true heading of 310. The other bit of information that this little page will give us on the CX3 is ground speed all the way on top. So my ground speed is going to be 86.95. I'm going to call that 87. We're going to fill that in right here. Boom. Okay. So we don't need the CX3 to fill out the rest of these three boxes over here. All right. So we now have to convert from true heading to magnetic heading. To do that, we have to take into consideration that magnetic variation. How exactly to find that? Does anybody know how we find magnetic variation?
Are there like lines on the chart for that?
There are, yeah, more exactly. We have these things called isogonic lines on your sectional chart that tell us what the magnetic variation is. Luckily for us, there's one that runs right through Scranton, our destination. Look at this right here, this kind of dashed magenta line, and it'll tell you what the variation is. 12 degrees west. Now, this is where that little phrase that Andrew brought up earlier, east is least, west is best, can help us out. So we add any west and we subtract any east variation, right? So we use that number 12. And since it's west, we're going to add 12. So I'm going to write plus 12 over here. So 310 plus 12, that's going to give me a magnetic heading of 322. One more step to find that compass heading, right? That's our goal. What do we have to do in the airplane? So to get from magnetic heading to compass heading, that's that deviation again, right? Anything that's screwing up the compass in the airplane, like your radios, right? So like we talked about, there's a little compass correction card. This is what it looks like in Mike Charlie. So for example, it's telling us if you want to go 120, you've actually got to steer 121 in the airplane. Our magnetic heading is 322. The closest value to that is 330 here on the bottom. It's saying for 330, you steer 330. So and in this case, our deviation is 0. Lucky for us. Okay, so at the 0. And finally, we get a compass heading. That's your end result is 322. So that's what you're going to fly there in the airplane from Princeton to Top of Climb. You're going to do 322 compass heading there. All right. So now that we filled that in, we got from true course to compass heading, we repeat this process for everything below now, right? We're only having to do this once actually, since the true airspeed just changes. But I think everything after that, it's going to remain the same winds and same true airspeed. So we're going to follow that same formula. Since we're doing a straight line here for all the checkpoints, it's going to still be the same true course, right? So 320, but we're going to use that 102 true airspeed now. So let's go back to the CX3. We're in the right thing before. Let me clear this all out. All right, and we're going to fill that in. True airspeed is 102. True course is again 320, and we're going to use the same winds there. 16 knots, 205 is direction, and we get all of our outputs again. So this time, the wind correction angle is only 8 degrees to the left, which means our true heading becomes 312. So let's fill that in here as well. So -8, true heading 312. And then the other bit of information that I'm going to get from this CX3 on top here is ground speed. Oh, pretty good, 107.73. So we're going to call that 108 knots for ground speed. Type that in there. Okay, and then remember, the rest of these we can fill out without the help of the CX3. So the variation is going to be constant throughout this. We're going to use +12 unless, again, you go into another area which has a different isogonic line. 312 plus 12 is 324. We had the same compass correction card. It's nothing again, so 0 for deviation, which means my compass heading is 324. So now from top of climb to Spruce Run, I want to point the nose in 324, and that should get me in the right direction there. So the rest of this is going to be the same, right? Since we're going to plug in the exact same thing, same winds and true air speeds and the courses, right? So I'm just going to copy this all the way down if I can figure out how. Let's see. Does that work? Okay, excellent. So that's all of our headings figured out there. We've got compass heading. Excellent. Okay, so we're going to continue filling this in again, left to right. So if we look back at our Excel, the next thing is this distance column, right? So usually this is pretty straightforward. You just use your plotter to measure, distances on the sectional chart, and you fill it in nautical miles, right? It gets, I wouldn't say hard, but it just gets a little more. We got to think a little bit more, at least for like the top of climb and top of descent stuff, right? So how exactly do we figure out this top of climb stuff? Let's go back here. So I said, now that we have the ground speed and duration for your first leg to top of climb, we can actually use a CX3 to determine distance, right? There's a relationship between distance, speed, and time. If we know two of the variables, you can figure out the other, right? So for the first leg, we know we're going 87 knots and then 7 minutes. So why don't we enter that into the CX3? There's an airspeed function. Ground speed is what we're looking for, ground speed function here. And we're going to fill this stuff in. So our ground speed for the first leg was, I believe, 87 knots. And our duration was 7 minutes. I'm going to set the units here to 7 minutes. Let's see. All right. And it's telling us 10.15 nautical miles for the distance there for your first leg, right? It doesn't have to be super precise again. We can just call it like 10.2 for now. So distance for Princeton to top of climb is going to be 10.2 miles. Now to figure out from top of climb to Spruce Run, pretty simple. We just measure the distance from Princeton to Spruce Run and subtract 10.2, right? So if I go back to SkyVector, I think it'll tell us right here. I'll just kind of use like a rough number for now. 19 miles, right, from Princeton to Spruce Run. So 19, let's see, minus 10.2. My brain is a little too slow to do some math right now. Okay, 8.8 is going to be the number, right? So 8.8 miles from top of climb to Spruce Run. So now for the rest of these, we would use your plotter to continue measuring distances, but we're going to use SkyVector here. I think it's 20 miles from Spruce Run to Bangor, and that's 16 for the next. So let's fill that in. All right, and then over here, 2 more that we're not going to fill in, right? So we have this top of descent checkpoint, top of descent, right? So we have to figure out how far from the airport we begin descending. There's not a chart in the POH, but there's a little formula we can figure out, right? So the first thing we have to determine is how much altitude do we actually have to lose? So we're going from 4,500 and descending to pattern altitude of 1962. So I'm going to subtract those two numbers here, and it's saying, okay, we only have to actually descend 2,538 feet. Now take that number, divide it by 300, and this is a pretty good rough estimate of like the distance in nautical miles to begin descending. I got 8.46. I'm going to round that up to 9 miles and say top of descent should be 9 miles from Scranton. I can work backwards the same way here to find the distance from Mount Pocono to top of descent, right? So let's see, 19 miles again. 19 minus 9, that's nice and easy there. So it'll be 10 miles from left of Mount Pocono to your top of descent. Excellent. So we've got all the distances now filled in, right? We also just copy all the ground speeds down here since we had it. The same exact ones. Okay. And we're going to continue now going into the right. So I think that's the next step as well, right? We've got our distances and we're going to look for times now. We're at step 16. Okay. The same thing with that relationship, right? Distance, speed, time. For the rest of this, we have distance, we have speed. Now we just got to find the time, and we use that same ground speed function on the CX3, right? Before I do that, something in the chat. My climb table is only set up for max gross. If I recall correctly, the 172 POH is the same weight, which is correct, yeah. Isn't the actual weight going to be a huge factor on the actual distance for top of climb? All right, so yeah, that's a very good point to bring up. Yeah, all the charts, most of these POHs, they're going to be for max crew. Some of them will have, for different weights as well. That's kind of the thing with this stuff. It's never going to be perfect. So we're just going to use the numbers here. That's why when we do this cross country flying and everything, it's always a mixture of what we call dead reckoning, which is what we're doing here, calculating headings, and then pilotage, looking outside that window, going to different checkpoints. So, we're never solely relying on this because, yeah, it's probably not entirely accurate, but it is a pretty good reference. But yeah, that is a really, really good thing to bring up. Very, very good thing to bring up. Okay, so getting back to this, we're going to figure out the rest of the times here. So CX3 ground speed function. Let's clear all this out. So again, we have distances and ground speeds. First one was 8.8 nautical miles. Ground speed is 108 knots. Fill that in. Duration is 4 minutes and 53 seconds. Now type that in here. And then we continue this process all the way down. So then I think next is 20. Same ground speed. 11 minutes and 6 seconds. All right, we got 16 and 10. All right, that's going to be 8 minutes and 53 seconds. Sometimes what I will also teach as well, if I'm not doing this on a computer like this, it may be easier to round the times later on, maybe to like zeros, 15, 30, 45 seconds, just so it's easier to add. Just a suggestion though. All right, we got one more here. So 9 nautical miles at 108 ground speed. Beautiful. That's going to take exactly 5 minutes. Okay, and we've got the times all sorted out. And one of the last things we're going to do here to finish up is the fuel consumption. We calculated earlier, okay, based on that cruise performance table, 7 gallons per hour. And now we know the times, right? So now we're just going to fill this in here. There's a fuel function as well, right above on the CX3. So let's use this. We're going to look for the volume, but we have duration and rate. The rate is 7, and then duration for the first leg is 4 minutes and 53 over here. Joe said, I suppose you could build the time distance formula into the spreadsheet. Yes, exactly. You definitely could do that. You don't need to use the CX3 for that. Something else I point out, it is a pretty simple relationship. So if you want to add that in, go for it. Yeah. Okay. We already have the fuel consumption read for the top of climb. So we're going to continue here. 4 minutes, 53 seconds. We're going to set the units. All right. And then 7 gallons an hour. Oh, of course I typed 8. Okay. 0.57 gallons. I'm going to round that up to 0.6 here. Yes, exactly. Don't forget your 1.1 gallons for engine start. Exactly. So I have that written down. Let's see, right over here in bold. Note that you should add 1.1 gallons. Sometimes what I'll do, I'll write it in like the notes section, but I'll also will include it at the end, like in a blank box. Good point there. All right, and we're going to continue down. 11 minutes and 6 seconds. And we're going to still use that 7 gallons an hour. This is 1.3, nice and even number. Okay. All right, while I do this though, does anybody have any big questions about what I've done so far? All right, guess not. Okay, so almost done. 0.7, and then we're going to do 5 minutes for the last one here. Okay. Cool. 0.6 again. And then, yes, exactly, Joe. So what we're going to do here, I like to just add this 1.1. So we know we're going to add that for the engine start, taxi, and all that. Okay. So now we filled in all the fuel. So if we go back to this, we are done with the fuel, right? And now step 18 is to add up totals for everything. So there's like 3 totals on the bottom we can add up here. Again, I added a little formula here for Excel, but we added up the distances. Turns out it's gonna be 74 miles to get there total. All the times add up to 42 minutes, 25 seconds. And then our fuel consumption, 7.1 gallons, which includes that 1.1 for engine start, right? So we're doing this at 9 p.m. Let's call this nighttime. Does anybody know how we're going to figure out our VFR reserves? How much extra fuel do I have to carry here? Anybody know the answer to that?
Yeah.
45 minutes for night, right?
All right, something. Let me see. I think a couple of people looked at it once. Anyone want to say at one time?
get it, Sarah?
Yeah, sure. It's to like your first major waypoint plus 45 minutes at cruising speed.
Yeah, so we're looking for an additional 45 minutes at normal cruising speed. You got it. How do we figure out how many gallons per hour that is? Well, we know we just calculated 7 gallons per hour. So if I multiply 7 times 0.75, I get 5.25. So I should add an additional 5.25 to that 7.1, which means 12.35, I guess, would be like the minimum legal requirement there to meet the reserves. All right, so that's for totals. And kind of the last thing that we would do here is to fill in like the airport frequencies on the bottom over here, right? We can use the chart supplement for all this information. So departure is Princeton and destination is Scranton. Don't have an ATIS, don't have ground, don't have tower, but departure, we can find this here in chart supplement as well. So if we go to Princeton, I'm gonna open this up here. Okay, here's Princeton. So there's going to be a communication section right here with our CTAF. Unicom is on 122.725. New York approach and departure control 132.8. So we're going to write down that frequency. If any of you guys have actually done this or are experienced with that, they're probably not going to pick you up 132.8. You probably have to go into Allentown. But for the purpose of this, we're going to write that down 132.8. CTAF we just saw also was 122.72. Same with the Unicom, we can fill that in. And field elevation, we can also find on the chart supplement or the sectional, 120 feet. We'll continue this here for Scranton, right? So why don't I go back here to the Scranton chart supplement. Okay, so communication is a little bit more since this is a towered airport. Okay, ATIS 111.6, we'll fill that in as well. We've got an approach frequency as well. It could help run this down if you're not getting flight following, right? So for approach, they've given us 2 frequencies, 120.95 if you're coming from 280 to 100 heading. So I guess that would be like the northern side, and then 126.3 for the southern side. So why don't we write that in? Could be different, who knows though. Tower right here is 120.1, ground is 121.9. We don't have a CTAF. This tower is actually full-time. Unicom for any fuel if I need that, 1295, and the field elevation was 962 there. So very helpful to kind of get that airport frequencies all in one spot. The last thing I wrote here, sometimes what I'll do is also draw a little sketch or diagram of the arrival airport, just so I know where I'm coming from or what the runway should look like. So for example, if I go back to SkyVector here, I should be able to pull up the little airport diagram. I'm not really sure I can draw this in Excel, but why don't I just take a little screenshot of this here. I'm going to paste this in Excel. But usually, when this is printed out, I will just draw maybe like 2 lines for these runways, label them, maybe somewhere on the margins. And what I like to do also is to draw an arrow from where I'm coming from, so I know what the airport should look like in terms of how I'm flying there. So if I go to, all right, where am I at? Shapes, arrow. 324 was my compass heading, so I could approximate maybe like something like this. So I should be able to anticipate if they say, let's see, join right down for 4, I should be able to kind of figure that out based on that line, right? So just something helpful. I mean, totally up to you if you're, want to practice drawing those out and figuring out how to enter the pattern, but just a useful tip there. All right, so it looks like we've got everything filled out. At least this is what I'll teach here, filled out in the cross-country nav log. That's going to complete our process there. So does anybody have any questions for me now? All right, Joe says, my last trip from Rochester to Princeton included a descent from 9,500 feet, which gave me either a bit shorter time, higher ground speed, or reduced fuel burn. Not including it to AVP is conservative, which is good, but from Rochester, there's a bit of a difference. Again, yeah, like a lot of this stuff, we can plan all we want. It's not going to be exactly what we see on this sheet. We just do this as a good reference stuff. So yeah, realistically, it could be a little bit different. All right, any other questions?
It's Joe again. Earlier on, you did a calculation where you divided by 300, I think.
Yes.
Where'd you get the 300 from? I didn't catch that.
Yeah, it's just like a rule of thumb that was developed. That's not my, I don't know where I found it, but that's like a shortcut formula you can use to calculate, the top of descent. All right, any other questions?
Seems like you did a great job, Wesley. Nobody else has questions.
Well, that's good to hear. Oh, I got one more thing in the chat, actually.
Oh, here we go.
Enval, very good question here. How do we know our chosen altitude is sufficient to clear all obstacles and terrain on our flight path? Okay, so when you go to your, I'll get back there, the sectional, you'll see different obstacles along your path. It'll tell you like the MSL and AGL, for example, right here, 1648. MSL, that can help. But also each one of these little quadrants has this big blue number. Your maximum elevation figure there is 2,800. So that's something you can also look for. That's a great question though, man. So yeah, if I was flying along, I see an MEF that's like 4,500, I probably, maybe just in case, do something a little higher. Yeah.
Anyone else? All right, Wesley, it seems like you're leaving us with some good sheets also to work with, which is really helpful. I like that whole list.
Excellent. Yeah, cool.
Thanks.
Glad to hear, of course.
Thank you. Thank you, Wesley.
You got it. All
Everyone
right.
for joining us today on our cross-country planning. Hopefully it was helpful. And after this recording, there's going to be a video up on the website that you can always check out along with the materials that Wesley provided today. So if you lose them or you need to find them, they'll be on the website. And next month, Wesley, are you back, or is it maybe John Beck?
Yeah, I'm not 100% sure. I believe as of now, I think we are trying to get John Beck to do some like check ride tips and everything. So I think that would be useful if he decides to do it. But we'll see. I haven't heard much about it yet in the recent weeks.
So stay tuned. If you haven't.
Yeah, exactly.
Not Sarah,
That's
not
something
Mark.
I attend to. Yeah. Yeah, exactly. Congratulations to you guys. Exactly.
Cool. Thanks, Wesley.
All
Thanks
right. Well,
for
yeah.
joining.
Of course. Thank you, everybody, for attending. Of course. Thank you.
And we'll see you all at the airport soon. Hopefully, happy flying.
Sounds good to me. All right.
All right.
Okay, thanks, Wesley.
Of course. All right. Good to see everybody. All right.
Thank you.
Good night.
You got
Thanks.
it. All right. Have a good night, everybody. Thank you.
Good night.
Have a good one.